Welcome back. The last video explained transaction records and their assembly into blocks of transactions. That video also explained that each node forms its own candidate block for the blockchain and competes with the other nodes to get its block onto the blockchain. This competition involves a process called mining. So let's fill in a few more features of the Bitcoin system and then dive into the mining process. The previous video described the blockchain as a bunch of serially linked blocks, where each block on the blockchain comprises a bunch of records of past Bitcoin transactions. Each block on the blockchain is linked to the immediately preceding block on the blockchain by a pointer that points to the immediately preceding block. In the diagram, this is shown by an arrow from each block pointing back to the immediately preceding block. And yes, every full node in the network includes a copy of the entire blockchain, starting from the very first block that was ever processed, called the Genesis block, right up to the top of the blockchain, that is, the most recently processed block of transactions. While the schematic node shown as node 1 illustrates block 126 as the top block, on the actual Bitcoin blockchain, over 900,000 blocks have been processed since the network went live in 2009. Since every full node stores every block that was ever processed, the blockchain contains every Bitcoin transaction that was ever processed. And since transaction records are not encrypted, anyone can look up the details of any processed transaction. So let's take a minute to look at an actual processed transaction record. This is the 41st transaction record in block 900,000 on the blockchain. You can find this record using any Bitcoin block explorer. I used blockchain.com/explorer and input 900,000 in the search bar to find this block. You will see TX41 at the top left of the record, followed by a short form of the TX ID for this record presented as a hyperlink. You can see the full TX ID by clicking on the hyperlink. The From field shows the TX ID of the input and the amount of the input. The amount is shown both in number of Bitcoin, BTC, and as a dollar amount at the then value of 1 Bitcoin. The input in this transaction record is much less than 1 Bitcoin and is set out to 8 digits. There are 8 digits because the Bitcoin system allows the transfer of as little as 1/100 millionth of 1 Bitcoin. A name was given to this smallest unit of a Bitcoin, 1 Satoshi. The name Satoshi is the name of the inventor of Bitcoin, Satoshi Nakamoto, although this may well be a fictional name. The To field shows 3 outputs, each with an address for the recipient and the amount to be transferred to the recipient. Note that most of the Bitcoin goes to output 3, which will no doubt be the change going back to the sender. The Bitcoin transferred in the 3 outputs is slightly less than the Bitcoin of the input, and this difference is the fee kept by the processing node. The upper right shows this fee in dollars and in sats, which is a shorthand for Satoshis. Recall that the address for each recipient in a P2 PKH transaction is a hash of the recipient's public key, so you can't actually learn who the recipient is. But wait a minute, couldn't you search for a particular address throughout the blockchain to see how many transactions involved a particular recipient? Yes, you could. However, recall that best practice is for a user to use a different public-private key pair for every transaction. So this will prevent snooping to find every transaction made by someone, and therefore increases privacy. It was also mentioned in the previous video that every block has a header. The header is where the pointer to the immediately preceding block is stored. But what is this pointer? It is simply a hash of all of the data in the header of the immediately preceding block. And recall, a good hash function gives a unique output for each different input. So the hash of the block header data of a block gives a unique reference number for that block that acts as a pointer to that block. So when a node creates a new candidate block for the blockchain that I will call block X, the header of the current top of the blockchain, block X-1, is hashed, and this hash is stored in the header of block X as a pointer to block X-1. If block X is the block that is added to the top of the blockchain, then a node in preparing a next candidate block for the blockchain that I will call block X+1 will hash the header data of block X to create a pointer to block X and store this pointer in the header of block X+1. Thus, these pointers chain blocks together to create the blockchain. Okay, so every node forms a candidate block for the blockchain and competes with the other nodes to get their candidate block onto the blockchain so that they can receive a reward. The competition uses a process called mining. In concept, mining is pretty simple. The header of any candidate block has certain fields that can be changed without affecting the function of the block. A target number is set, and the challenge for a node is to find values for the changeable fields in the header such that a hash of the block header results in a number that is smaller than the target number. Recall that a hash of data typically changes dramatically in an unpredictable way with even the change of 1 bit in the data. So a node has no idea how it needs to adjust the changeable fields in the header to get to a number smaller than the target number. Each node just has to keep changing the values in the changeable fields and see what comes out as the hash until, eventually, one of the nodes gets lucky and finds values of the changeable fields that result in a hash number that is lower than the target number. Let's say node 1 finds values for the changeable fields in the header of its candidate block, such that a hash of the block header results in a number less than the target number. When this happens, node 1 adds its candidate block to the top of its local copy of the blockchain as a new blockchain block, and also sends its new block with the successfully adjusted changeable fields to the other nodes. These other nodes check the calculations, and if they agree that the target has been met and the block also passes a number of validity checks, will add the new block to their local copy of the blockchain and pass the block on to yet further nodes. In this way, the new block propagates through the Bitcoin network as the new top block. This mining approach and subsequent validation is called proof of work, because a node has to work to find values for the changeable fields in its candidate block that result in a hash number smaller than the target number, and has to prove this work by sending its candidate block with its adjusted header values to other nodes for validation so that the other nodes can verify the node did, in fact, successfully mine the block. But wait, the nodes are in competition. So why is a node prepared to add another node's block to the blockchain? This is because it is in a node's best interest to do so, as will become apparent shortly. Once a new block is added to the top of the blockchain, the transactions contained in the block are considered to be completed. Earlier, when a node formed its own candidate block, it did not change its mempool, but instead added copies of transactions from its mempool to its candidate block. Now each node looks at the transaction records that are included in the new block on the blockchain and deletes those transaction records from its local mempool. Additionally, for each transaction record in the new block, each node removes from its local UTXO database the previous transactions that funded the Bitcoin spent by the transaction record. That is, the inputs to the transaction record. And it adds to its local UTXO the transactions where Bitcoin was transferred on. That is, the outputs of the transaction records. In this way, the mempool and UTXO of each node is kept up to date. With a new block on the blockchain, future transaction records can reference transactions from the new block, shown as prior transactions J, K, L, and M in the diagram, in order to spend Bitcoin received in the transactions recorded by the new block. Mining gets its name from the block subsidy, which is the Bitcoin awarded to the node that gets its candidate block onto the blockchain. In fact, the block subsidy is the only way new Bitcoin is created. You may recall that the block subsidy halves after the processing of every 210,000 blocks. In consequence, after enough halvings, the block subsidy will drop below 1 Satoshi, which will round to 0. At that point, no new Bitcoin can be created. You may have heard that the maximum number of Bitcoin is 21 million. This is a consequence of the halvings of the block subsidy. The next video explains how the mining target is set, how mining progresses, and how ties are resolved. You can find the next video by subscribing to this channel or by clicking on the above link.